All right, great. Hello, everyone. Welcome back to another episode of Effect Time. I've lost track of the count at this point, but we've already done a few, and we're just getting started on all of the topics that we still want to tackle. And I think today we're talking about a fairly fundamental topic of effect. One of the core primitives that most of the effects ecosystem is built upon, that I actually shamefully know very little about up until hopefully today, where hopefully learn a lot about this. So we're going to talk about the concept of fibers. Fibers is also a concept that the effect twin project Zio, I think, heavily uses, and where this was inspired by and modeled after. But I still don't know what a fiber really is. All I know is roughly the kind of problem it's trying to solve. And I think that problem is also somewhat familiar to most other JavaScript and TypeScript developers. So I briefly want to motivate that, and also just want to say hello to our special guest today. We welcome back Max, who we've had on a few episodes ago, where we've talked about Effect CLI. And we also have Harry here. And the four of us, together with Mike, Max, and Harry, we're also working on another little project that we might talk more about soon, where we, of course, use Effect. And throughout our collaboration there, we stumbled over the question, okay, what the fudge are fibers? And so Harry, I think, really motivated that question. So yeah, before answering that question, let's briefly dive into the broad problem space that fibers are about. So let me briefly share my screen, and afterwards I'll hand over to Mike again. So depending on how long you're around in the JavaScript ecosystem, then you might be somewhat painfully familiar with callbacks. Callbacks everywhere, and callbacks is basically back then the only mean to asynchronous programming in JavaScript that we had available. And this looks somewhat tame and innocent, but these sort of callbacks, this was like your only way how you deal with anything that runs asynchronously. So you wait for it to be called back, and then you nest it, and then you have like a very deeply nested kind of thing. And that later was known as the callback hell. So I remember this very vividly, and it was a distinct time. And then as an evolution of that, we got async await based on promises. Or first we got promises, really. And then on top of that, syntactic sugar with async await, where we could just wait for something to be returned. And as long as we're in async context, we can simply say await. And we have a simplified way of like modeling our asynchronous code here. And we can even do error handling using try catch, which we know has a couple of limitations as well. But that's roughly the evolution that we had, going from callbacks to promises and async await. However, there are also some limitations around this, and where it's rather rigid than flexible. And some that doesn't quite allow you to model your applications in some of the ways that you need to. And this is the kind of problem space that fibers try to address. So at that point, I might want to hand over to Michael, or maybe Mike, you can elaborate a little bit on like what are some of the limitations that we have available right now with async await promises that fibers try to provide a better primitive and abstraction over. And then we can see a little bit how they function, how they enable other primitives on top of it. And once we dug into this, then we can, once we have a bit of an understanding what the current implementation of fibers look like, then we can hand over to Max, who happens to work on the newest generation of fiber implementations that I think is also inspired by the newest generation of fiber implementations in ZIO with ZIO2. But first things first, let's get a good understanding of what the first generation of fibers look like.
Great, so let me start on my screen share. Let's see. There you go. We start with a very nice console log asking what is a fiber. So as you correctly explained, one of the key problems that fibers try to solve is the problem of concurrency and the problem of asynchronous operations. The concept of fibers, they start as lightweight threads in multi-threaded languages, multi-threaded ecosystems. Threads are very expensive, and up until the point where fibers were really developed around the ecosystems, the only way you could do concurrency and parallelisms were using threads. Using threads are very expensive, so spawning the new thread is an expensive operation in terms of memory allocation, in terms of CPU resources, and anything else. And really on a custom, on even a very good hardware, it's very rare that you can spawn more than 1,000, 2,000 threads.
Right, and you're talking right now about like something like Java, Scala.
Precisely.
Right.
Any type of language
at this point.
Yeah, they are way bigger than JavaScript itself. So the problem that fibers are solving is the problem of structured concurrency. So generally, a number of operations that may run in parallel when possible, given the language and the hardware, or that are scheduled on the same thread. But the idea of the fiber is literally very similar to the idea of a thread. Now, in JavaScript, we are used to the async await pattern in dealing with concurrency, but let's make a few examples. Let's take something very simple. That's for example a promise.all.
Got it. So that basically means for people viewing and who might just be experienced with JavaScript, there's like this sort of like a light version of a more general conversation about fibers. So we could have the same conversation about fibers in Scala, for example, where it's truly about like concurrent, like multi-threaded computation. Here, we're just dealing with like normal JavaScript runs in one thread. But we still get a lot of benefits from the abstraction that a fiber is in the context of single-threaded JavaScript.
I would say that more generally, anytime you have asynchronous operations, you can still have concurrent operations in the same thread.
Yep.
And it's what we are trying, for example, to show here. You can do a promise.all, which will wait for all the promises to complete. Let's say I do a fetch of API1. I do a fetch.
And like promise.all is something I think many of us use very heavily before diving into effect. But like that's one mean of like doing something somewhat in parallel, waiting for it, and then doing the next thing. But there's also like, I think there's like now promise dot, like I think there's like alternative to all that.
There's all settled, there's
all settled,
raise.
Right. Yeah, there's a few of these, and they try to solve like particular use cases, but there's still many use cases kind of like left like to not so great result. And I think this is where we have many more options with effect.
And here with for example promise.all, the idea is I want to run all of those operations in parallel. I want to wait for the result, and in case any of those fail, I want to complete the operation with a failure. So I only care about the result if everything is completed. Now, here, let's make the hypothesis that those 3 requests starts in parallel, but then the second one fails straight away after, for example, 20 milliseconds. Do I really want to wait for the rest to be completed before returning? Probably not. In fact, promise.all gives you the results straight away at the time, kind of first failure. But the other 2 are never getting interrupted. The requests are never getting canceled. So you're still doing stuff behind the scenes. Let's think about, for example, if these, instead of being a simple fetch call, there were each operations that take roughly 10 minutes to execute, and they perform a lot of work, you will be doing a lot of unnecessary work, and this work is never properly cleaned up. With fibers comes the idea of suspending computations, so computations that can be halted at any point in time, and not only they can be halted, they can even be interrupted. And when a fiber is interrupted, a cleanup procedure runs. So effectively, I will be able to specify an equivalent of something like that, where at the first failure, not only I return straight away, but I also go on and cancel the remaining operations.
And just to be clear on the distinction between halted and interrupted, does halted mean like whatever you're trying to do, if that is composed out of like 10 sub steps and it's right about executing step 2, then and you say halt, then basically waits until it starts with the execution of step 3 until it's continued again?
The idea of halting a computation, another way to put it is called suspending an operation. Think, for example, about the React 18 and the whole suspense idea. You want to do concurrent things.
Got it.
When you have a big, large synchronous operation that takes over the whole thread, it's not really a good thing because the UI gets stuck. You want those operations to be suspendable so that they can pause, something else might execute, and then you get back to it. So that's how you efficiently schedule fibers in a single thread. And the concept is extremely powerful, because I would go on and say that fibers are even more useful in a single threaded language compared to a multi-threaded language. Because in a multi-threaded language, you have like choice 1 and 2 in how to do things. In JavaScript, you can't stack a thread.
Right.
You have only one.
That's a great point. So just to recap at the current point, so what we're aiming to get with fibers, this new abstraction, is one, help with error handling, where we basically can say, okay, API 2 can fail here, what to do about API 1 and 3, and like how should a user interact with this? Should the entire thing fail or not? So more granular error handling than just like one big try catch around all of it. Then another is cancellation. Maybe some of us have dabbled with like the what is called the abort controller to implement this, but that gets verbose and painful pretty quickly. So that's another aspect that this is trying to address. And then the suspension. So okay, that makes total sense to me. That's great.
Okay, so I think we have enough motivation to realize that fibers are definitely an interesting topic. But before we get into the details of how a fiber looks like, we gotta speak for a few minutes about what effect is, and in general, what an IO data type that can run inside a fiber looks like.
Right. Since I've used effect now for quite a while, and I've never had to use like a fiber explicitly. So my understanding is that effects are implemented on top of fibers. So you'd rarely get in touch with them like too closely in most cases yourself. but it's good to know that this is like the underlying primitives that are being used here.
They are definitely a lower level primitive that, depending on the context, you may want to use them directly, but generally speaking, you have higher order combinators that are implemented in terms of fiber behind the scenes, and you don't need to take care of them directly. I will not do the full effect. I will try to be as small as possible, but something needs to be cleared up from the very beginning. What we will do is we will simulate a small effect type that has a single parameter that just represents the output of a program. We are going to ignore the error channel and the environment channel for the purpose of keeping this discussion a little bit more contained. An IO data type in its simplest form could be encoded as something like that. And if I were to make it asynchronous, I could encode it in for example, this way. That's and just an async function.
Can you just provide a few analogies of like what IO stands for in this case?
Input, output.
Got it. So you put in an argument, you get something back?
It's meant to represent any type of side effect that can run. It's literally like console input, output. And you could call it effect or computation or program. IO is just short and quick. If we implement it this way, we're not really gaining anything because we are based on top of promises. Mm-hmm. So we sort of want to avoid that type of thing. Now, there are two ways of encoding data types. One is this one, which is called the final encoding, where the program is directly executable. The other one, it's called the initial encoding, where instead of writing something that's directly executable, you write it as the primitives that it supports. So we might say that an IO of A, it's, for example, a sync operation of A, or can be an async operation of A. Let's begin writing those two. Plus sync up of A. I'm just going to implement a simple tagged union. Sync up.
And the reason why you're using classes here is, I think, because it makes it a little bit easier, because you don't need to differentiate. Like, classes give you a thing in TypeScript that both works on a type level and on a term level. Otherwise, there's other than that, there's no particular reason to use a class here, I think.
No, it's simply because there is a constructor for free,
right?
Fundamentally. Here I have to use one trick. The most obvious would be to actually use the A parameter. But let's begin like that. The next operation will be more complex. So let's say we have one sync, one async. Sync. This doesn't return an A, but we might say that this, for example, is a callback, old style callback callback thing. And
yeah, I think an interesting note on the callback. So I don't know the performance benchmarks on the top of my head here, but I think I remember that using promises and async await comes at quite a performance penalty, and that using callbacks can be faster. So maybe we find something that backs this up, but that's what I remember.
You are perfectly right. There are two performance compromises that you make. The first one is from callbacks to promises. The second is from promises to async await. Because async await is commonly known as a syntactic sugar on top of promises, but that's a false statement.
Oh, okay. So I've already
clarify,
worked out some wrong stuff here.
Do you mean wrapping the callback style with promises so that it's compatible is the first of those two that you mentioned?
Yes.
Gotcha.
That's the first performance hit. The second performance hit is when you express the computation in terms of async await, because behind the scenes, what's going on is async await is implemented using generators. So they are literally the same thing as iterable computations that by nature are slower, even though they're getting better and better, but there is definitely a performance cost.
That's a great point. I remember before async await were like readily available in modern browsers and Node, etc. And you used Babel or these kind of tools, and you looked at the transpiled where you were already able to use async await, and you looked at what is Babel actually producing here. It was using exactly that. Or I don't remember whether it was using generators or compiled it in some callbacky thing, but I remember that rings true.
Okay, so this is the very basic definition, and with this we can already make something like sync of a, mixing the syntaxes, obviously.
Okay, so you're building yourself a little DSL here that gives you an alternative. This way you can get to build programs like we had before with like promise.all, etc. But instead of using promises, we drop down again to how everything is implemented using callbacks. But we get to build ourselves like nicer primitives to work with that eventually, I guess, like the full the end form of this will look like fibers. So these are baby fibers, I guess.
This is just a representation of a computation.
Got it.
That's not yet a fiber.
Okay.
So the next thing I want to do is like that. I can already say something like console log. Okay, and I could say async, and that's the complete. And I can say, for example, fetch whatever dot then result complete result.
Ignoring for a second that we use promises here under the hood, but yeah.
Ignoring the fact that behind the scenes we're using promises here. Once. We see that in both cases we have, okay, on one side we have this is a void, and in this case we have unknown, because like promises in this style, in the callback style, when you define things you have to specify manually the result type. Like this would be an IO of what? A result, a response.
Yep.
Response. And we have our IO of a response. This is effect like thing. The next thing you want to do is composing those two things. How do you compose? Well, you make new primitives. So like one primitive could be flatMap of A. And here it's a point where we have to stretch a little bit the type system. And you're gonna see why. Tag, so that's a flatMap. constructor read only self, which is an IO of what A, and a function that continues from the A to some sort of IO B. This will look like promise.then. You want to concatenate operations. Now, here, first problem. We have two type parameters, and in the IO, we only have one. So in general, what we would need are a thing called GADTs that TypeScript doesn't have by default. So we go on and force the type to be used, and we literally erase all the type information. So that's preserved for fake reasons, but now we can say export function, flatMap.
So functionality wise, this doesn't have to, like, there's nothing in runtime that, like, the trick you've like described here doesn't do anything. This is just to work around some TypeScript limitations and basically simulate like it had more generic capabilities.
Precisely. Because flat mapping a promise that returns a response with a promise that returns a string, we'll end up with a promise that returns a string.
Okay. This has nothing to do here with like fibers or like this DSL you're building here. It's just a TypeScript trick.
This is just a TypeScript thing. So F, of course, the compiler will complain, rightfully so, I would say. Lucky for us, TypeScript is quite unsafe. You can do as any, and you're good to go. So now we can say flatMap, say our async op, which we transform to a URL string. Instead of saying whatever, we have our URL, flatMap, sync operation, whatever. And here we see, we continue from a response to something else. And let's say we want to log it. We want to say response and sync console.log response. Const result. And this would be an IO avoid. One key aspect here is the callback hell, which is more theoretically known as continuation passing style, is a model that can encompass both synchronous and asynchronous computations.
Right.
Because you pass a callback, you don't know when that callback gets invoked. Could be invoked straight away or could be invoked as a delay thing. So you have a single model that encompass both words. Promises and async await are kind of weird in separating the meaning of code. You write code in a different way if it's synchronous or if it's asynchronous.
Right.
With fibers and structural concurrency and effect systems, you get back to a model where you treat computations in the same way. You write sync code and async code that look exactly the same. But here we are at the point of asking ourselves, okay, now we have our nice DSL. Nice, I don't know if it's nice, but probably the API could be improved. Like, this is not a good flat map. I could add a few. I'm in the new branch where there's TS+, so I could turn this into a nice syntax in a matter of a few minutes, but that's not the purpose of this discussion. Now that begs the question, how do I run this? How do I execute this thing? So this is pure description. I haven't really said anything about execution. I can't directly execute. There's nothing I can call here. when this flatMap, if I console log this result, which is actually a good thing to do. Why is it? It's complaining because I need leave done. Doesn't yet know that fetch will become part of node. Build demo, CJS, index.js. We are logging what this is. It's literally a class instance that represents the composition of two operations. So how would we implement a runtime for this? I could say export function, run, and what we want is something like we want to run an IO of A, and on done, we want to have our result A and have it as a callback thing. This will not return anything in particular. So now we could say run result. Okay, here I have a void. There's literally nothing I should do. But let's say that instead, I don't know, I want to say response headers, whatever. Remove them from the log.
Syntax, but yeah.
Yeah, I'm not doing it this way.
I think status text is good. But yeah, or
get whatever string or null, and now here I should have the exit value, and the exit value should be string or null.
got it. So we basically need to write an interpreter for that now.
We have to write an interpreter.
I just want to be a bit conscious of time here. So like I think we can. Should we continue?
I will not write the whole interpreter. I will just sketch.
Yeah, let's basically now we have like a new little toy DSL for like a unified way of like writing synchronous and asynchronous programs. So how does that get us to fibers?
Now the very own question: what is a fiber? Mm-hmm. I've said the computation shall be suspendable. That means I cannot run everything inside this run function. I could start by switching over self.tag and say, okay, in case it's an async op, I need to do something. In case it's a sync op, I need to do something. I'll not implement all of those because later on we see it in Mac's part.
Might it be worthwhile before getting into sketching out the interpreter to maybe do one more data type to represent parallelizing and then the cleanup that you mentioned, if we have time?
It would literally be a matter of saying all of A export class, all of A read only A. We're faking again the type tag all structure. Okay, let me make this easy. There is a better syntax where I could spread a tuple and have A be a union of potentially multiple things. And here I could say all response or undefined, because yeah,
We don't have a tuple, but an array.
we don't have a tuple, but we have an array.
I guess you could, after here, you could probably, yeah, or not.
I am bothered by this.
Oh yeah.
Would be almost offensive to not use all the TypeScript features, right?
Would be really offensive.
Why are you checking for the never case?
I don't think this knows. What do you mean, the never case?
Creating a single element tuple out of A. What does that do?
Oh, that.
No,
that
I'm sorry, I don't want to sidetrack us.
no, that prevents a union to spread out. This is a non-distributive thing. Given IO is a union, I don't want distribution.
Gotcha.
Now I can easily remove that. And this is now never. Lovely. Why it's never?
I guess because it's not just one A, but like you've handled a case of one, like a tuple of one, but
never. No, that's extend IO, infer.
I would suggest we undo this, and you gotta like
We get the idea of all.
Yep. Let's not get too deep here.
Oh, this was easy.
Okay.
We have two. No worries.
All right.
We're not getting killed by TypeScript here. But anyway, the idea is literally you describe things. Second point would be interruption. Here we don't yet have an interruptible primitive, but interruption would be another type of description. A fiber doesn't require to have interruption available. It's a very good thing to have, and we're gonna see in the effect fiber. The only thing that a fiber should have is suspension. So it should not take the whole thread. If here I were to make a concatenation of infinite synchronous operations, when I run this run, it should not take over the whole thread. It should yield after a while and get back. Which begs the problem. If this run is a simple function, when I stop my computation to restart at a later point, let's say this will have to be a while loop because we are traversing multiple operations. Flatmap have to do multiple things, and we don't want to implement this function in a recursive way, because otherwise the stack will blow up. We want to implement it iteratively while keeping the stack around. So here we would have something like a const continuation stack, which in its simple way, it's literally in this case an array of flatMap operations. Yeah, that's not TypeScript. And in here, when we have like a flatMap, say that let the current operation start as self. In this case, the current operation is going to be current.self. We want to continue while we have an operation, current equal current.self. This is an IO of any. And we want to say continuation stack.push self current. Why this is not narrowed down? Because of course I have to invert. So when we get to a flatMap, we push it on the stack for later on. When we no longer have a current operation, here we will start by pulling the stack and see if we have operations to continue. We pop from the stack and continue. If the stack is empty, it means we're done. But in this case, all the computation runs inside here. So if I have everything synchronous, it will be stacked. I should maintain let a counter, for example. This is one way. And saying while current or I is less than 1,000, and at every cycle of the loop, I increment this counter. So I don't do more than 1,000 operations on a single thread, and then I yield. And then I would have to say like set immediate or set timeout to schedule the continuation. But here the question starts, where do I keep my state around?
And the state here means like which operations do I have to do?
Which operations do I have to do and where I've left? That's two key pieces.
Right.
That's where a fiber starts.
And I just want to point out for those like watching and being terribly puzzled and thinking, oh, I never will touch effect because like I'll need to deal with all of like this madness. Quite the opposite. Effect has all of this nicely implemented, so you don't have to like. This is for the intellectually curious who want to understand how does this work under the hood. But you don't need to write a while loop or whatever, keep track of stacks. You can just write like nicely high level code. And this is just a magic that makes it work fast and reliable under the hood.
I think one of the things that Zio has done really well, and because Effect is modeled after Zio, we're trying to do the same, is that keep the framework very approachable for people who are just learning it. So you really don't need to learn much to actually use the framework effectively in your code. But for those who dive into the framework and learn some of the lower level operators and data types that we have, you can then do even more powerful things. But it really doesn't take much to actually get started with Effect and actually perform some pretty powerful operations just with the base primitives that are very easily accessible.
So if you have a class, which is an object with a context, you can isolate the continuation stack here and in execution, instead of doing this, I would have to say new fiber running this effect. That's the whole thing. A fiber is just that. It's a place where the state of a running async computation is preserved. That keeps in mind the continuation stack. So where to continue. Now, we could go on and implement literally a minimal example of this, but this set of primitives is already quite dumb, and we could pick up better primitives to make the interpreter even easier, but this is just for demonstration purposes. The idea of a fiber is literally isolating the state of a running computation inside an object that can be resumed at a later point. Because in this set immediate, I still have my fiber around. The context is still all available. And I could say, okay, set immediate or set timeout, and let's say start from 1 second later, I could continue. Where again, I could say that this dot current operation, it's the same as before. The stack is the same as before. I could say this dot run, and we continue. So that's the whole idea of a fiber, and I'll take any question. Otherwise, I hand over to Max to show the thing on effect, where at least we have a complete implementation of that. Go on.
I have a quick question. Can we relate this to React's implementation?
React's implementation is for backward compatibility, quite a weird thing. Instead of preserving the context inside a fiber object, you throw a promise. Like you have your component is like a normal function that can throw. If you throw a promise, there's an async band, there's an error boundary that catches the promise and say, oh, I have a promise. I should continue with the promise. When I'm done, I'm gonna render. That's how you suspend outside of the context of a single function. That's another way of doing things. I'm not gonna comment on the beauty of throwing promises, but it's one way of they had to preserve backward compatibility. They don't want the whole rendering thing to be completely blocking. When you don't want to block, you throw a promise that gives you this yielding, this kind of suspension. The whole idea of a fiber is a suspendable and resumable operation.
Awesome, thank you.
Get.
That's been super helpful so far to understand. And it's really like, I guess, effect and fibers are really like this sort of DSL around async or like general computational primitives that can be composed together. And I guess fiber is just a really powerful interpreter that makes all of this work.
It's at the end of the day a powerful interpreter.
Right.
In the case of React, it's a fiber implemented in a final encoding. In this case, it's implemented with an initial encoding. So things slightly different.
Got it.
Max, do you want me to share the workspace or do you have it locally?
I have it locally. I can pull it up here. Let me just open it.
All right, switching over to Max's computer then.
Switching over.
Harry, do you feel your questions have been answered to a satisfactory point from your curiosity around what are fibers?
Absolutely. This has been really fascinating.
Are you guys able to see my screen?
Yeah, we are, but please font a little bit bigger. The second question you asked before was why it's performant. It's all about minimizing allocation, minimizing memory allocation. And this is what gets really interesting in Zio 2.0 and the fiber that we have here, because it's very, very minimal in the memory that it allocates.
I expect it doesn't get simpler to understand though.
No, it doesn't.
It does not. And you know, there was a video that the Zio guys had done during one of their sessions at some point where they went through kind of something similar, where they just explained like fibers and like how they actually implement it. But what they talked about a lot is that at a certain point, you know, you have to become somewhat unsafe in your types and erase type information. So in effect does a very excellent job of preserving type information as you're using the framework. It preserves error types all the way up to the top of your application. And Mike actually did an excellent talk at Functional Scala about the benefits of TypeScript in that regard, and type inference and what we get. But what you'll probably notice looking at just even this little bit of code here is all of this any, unknown, null, like all of this really ugly, mutable and untyped code. And so, you know, as the Zio guys explained in their video, I'll explain the same thing. At a certain point, we have to sacrifice type information for speed and efficiency, and as long as the implementation is accurate.
Can we make it larger?
Oh yeah. Tell me when to stop.
All right.
Maybe
I think that's a really great point. I think that's big enough for me.
All right.
And I think it matches what Mike had. I think that's a really great point. And I've like when I model something for an application, and if that has like a sort of like a more user-facing part, I come to almost like duplicate my DSL in a way where I have like a more like a user-facing DSL that has generics. And does has like type inference, generics, etc. You hover over something, you see exactly, oh, this is the return type. But when you come to the implementation of it, it's the generics don't buy you anything anymore. And I come to basically almost duplicate that where I don't have a generic, but I just have the primitive types. Instead of like having a string generic that could be anything, I'll just don't even bother and don't make it generic, and my implementation just deals with that. And so that's sort of like an emerging pattern for me across projects, and seems similar here.
Yeah, I mean, like I said, as we kind of look through some of this, I'm not going to dive too deep into the fiber implementation itself, but I want to highlight all of the points that Mike brought up in explaining a fiber and how that kind of looks in the actual implementation. And again, all credit to the Zio guys for doing such a great job with their library as well. So happy we can borrow from them. But as you can see, like we have a class here that Mike explained that we're using to maintain our state. And in this case, we're calling it the context of the fiber, which is just an actual implementation of a generic fiber runtime, because you know there are other ways to implement this. But for our implementation, we have our fiber context class, and some of the things that Mike wrote in his basic implementation, I'll point out here. So we are maintaining some additional state related to our fiber, and the fiber state data type, which maybe I'll explain maybe in a second, is one of the ways that we track how the fiber is actually, what state the fiber is actually in when it's running.
Can you briefly describe which sort of states it could be in and how that relates to our mental model from before?
Sure.
Or is that not relatable?
No, I would say it's relatable. We can talk about it. So it's pretty simple. A fiber can either be executing or done. So it's relatively simple, but we encapsulate some information within the fiber state. I'm not going to get too deep in the weeds here. But the important thing is that, you know, a fiber can only be either executing its effect or its program, or it can be finished with and have a result for you. So when that fiber actually is joined with the program. When you create you can create fibers in effect by forking them. When that fiber is eventually joined, we wait for the result of that computation, and that would indicate that we'd have a finished fiber at that point. At which point we'd
and
get
just
the exit.
like forking here has nothing to do with like in C when you fork another process. So this is just forking in terms of whatever concurrency mechanisms you have in JavaScript, that you basically let it go, and it like there can be two different like flows in the application, and later on you bring them together again.
Right, forking a fiber in JavaScript essentially creates a child fiber of the current fiber that you're on. So again, I'm not going to talk too much about like how the hierarchy of fibers and like that type of thing, but I do want to point out like some of the other things that Mike explained when he was going through his basic implementation. So we talked about the state, so the fiber can either be running or it can be finished. The counter that Mike referred to, the operation counter, in our implementation, we call it the async epoch. It's basically just our counter for how many operations we've performed.
Certainly sounds fancier.
Much fancier.
That's actually the counter of asynchronous operations.
Right. And so we also have the stack that Mike pointed out here, implemented with an actual stack in this case, as opposed to the array that Mike had referred to. I'm not going to touch on scope at the moment because that kind of goes beyond the discussion that we were currently having. But Mike did write in his little implementation that there's the concept of a current effect or a current IO operation that's being executed. And so we track that in our implementation here with the next effect. I did kind of briefly mention that a fiber can have child fibers that are running with some information about the parent. The parent can track its children. And so we track the set of running child fibers in this children variable. And then
what is the utility of doing that?
The utility of having a set of child fibers?
Yeah.
You can Mike, you can correct me if I'm wrong here, but like you can sort of the way I conceptualize this is exactly kind of like what Johannes was saying. It's not forking like forking in C, but you can conceptualize it that way, is the way that I think about it. Forking a fiber, you can actually do things on the child fibers from the parent, like interrupt and things like that. But right. Mike can correct me if I'm wrong.
It basically gives you like a hierarchical structure to this. Yeah.
Now, to do things with the childs, you could do it directly in user code. The reason why you track the children here is to actually preserve one of the fundamental identities that have to be preserved. If you have a piece of code that spawns up to processes and then joins them back together, the result should be always equivalent to a process that never forked anything and never joined anything, like do all the stuff on the same program. To guarantee this, you have to guarantee that when a process is finished, all its child are also finished. You don't want to ever leak any fiber to the outside. So that's the reason you track them. So when something gets killed or completed, you can propagate the kill or complete to the childs. That's not always what you want to do. Sometimes you want to twiggle the behavior and forking into the parent, and that's what scopes are for.
Right. Yeah. And I'll probably, if we want to talk about what a scope is, I'll probably let Mike handle that. But it's nothing more than a way to group. As far as I understand it, it's nothing more than a way to group a particular set of fibers under a given scope, or to attach them to the quote unquote global scope, which is a concept in the effect system of like having a root scope object. The last piece of the fiber context state, or like, the things that we're tracking, is the actual runtime configuration of the fiber. So you have the ability to provide a certain degree of configuration for how a fiber is actually going to execute. And you can actually swap out pieces of the runtime configuration at runtime, which is pretty interesting. So you actually have access to the runtime config and can manipulate how effects are actually executing at runtime. But just to kind of like give you an idea of what's being passed in here, we're still kind of debating the concept of fatal errors in effect, but you have the ability to handle specific errors that are designated, that you can designate as fatal. So you're passed in some defect and you can say this is a fatal error, and handle it somehow. You can also report on that fatal error. But again, this is not the final API of our next branch. So I would take the config with a grain of salt at the moment, because we're still iterating on it.
But most importantly, you see there is a max op, supervisor, and loggers. Max op is the maximum number of operations that run in a fiber. Our hard-coded 1,000 before, that's configurable. Supervisor is somebody that basically supervise the processes that you're launching, and that can be used to track the whole program. When you fork new fibers, they are getting reported. Think about, for example, if you want to implement a metric system on top that keeps track of running processes and et cetera, that's via supervisors. And loggers, as you might imagine, are to log operations.
What
loggers,
would happen if you exceed the maximum operations?
If the fiber yields, suspends.
And okay, so it basically just waits until it catches up with more work and so it frees up?
It literally does a set immediate. So it releases the thread. So if there is anything else that need to run, the other things run. It's just like when in a UI, you do set immediate because you want to continue your work, and at the end you want to restart.
Right.
Yeah. And then Mike pointed out the loggers. This is a feature in the next branch of effect, and also in ZO 2.0, logging is baked in. So we have the ability to do some cool stuff here. And then the one last thing I'll just very quickly mention is there are different runtime configuration flags that exist in our next branch of effect. And they basically just allow you to do certain things. I think maybe the two things that people could conceptualize is turning on and off the, we haven't implemented this yet, but in ZO, enabling the log runtime allows somebody to, it's kind of like a debugging tool. It allows people to log every single effect that's executed. It logs out like the name of the instruction that was executed and what it was executed with. And so we're working
the trace that originated from.
Exactly. So you get some kind of useful information here. But anyways, the runtime configuration is basically, like I said, a way to turn on different ways of manipulate the way that a fiber executes. So now I'm going to skip all the way down to the very bottom of this very large file. So Mike had showed you guys kind of like the way that a fiber is, the instructions are actually executed on a fiber. And the interesting thing about fibers in effect is that in reality, what's happening is every instruction that gets passed in here, and by instruction, I mean an effect, right? We think of its effects in terms of, like Mike had showed us, kind of like a tagged union of different data types that we can then use to perform different instructions. So when I say run an instruction, I'm talking about running an effect. But really what's happening here is a giant try finally loop, or try finally execution here. And inside here, there's the while loop that Mike referred to that basically checks the current, what's going on with the current effect. And then we have a separate do while loop in here.
As an operation count, as you see.
That tracks the count of ops that are actually ongoing and performs at least one effect and then continues while the current effect is null. And this do while loop in here is actually where we evaluate the different instructions and what to do with them. So you can kind of get an idea of, like Mike was saying, there's kind of like an interpreter here where we're taking an effect in and we're interpreting what to actually do with that effect. And then after a certain set of operations, we yield that fiber to other fibers that might need to execute in the runtime. And we track, and again, all this state is tracked by that specific fiber. So we still have a lot of work to do on our implementation here, but there are a lot of interesting pieces already in our system next branch that we're very excited to get out there for people to test. So
I guess this is the proof that every functional system is built on an imperative system.
that is the proof. And then
That's
actually the one
proof.
last
Do you
thing.
have any go-to statements and labels hidden in here as well?
No, but there are two try blocks. So the outer try block is really to figure out like what to actually do in the case that anything inside the execution actually fails. And the inner try block is what is interpreting the effects. And in the case of any specific types of failures, we may do certain things. And then we obviously have the like catch-all situation where we would use the actual runtime to determine if the error that was thrown is fatal, and if it is, report it and do something with it. At the moment, this is totally incomplete, but yeah, we still haven't figured out if this is going to stay around in our implementation or not.
Got it.
And here the second key point, you've seen it mentioned, interruption. There is a tricky bit, which is, okay, if I have something that triggers an interruption, that's not the last operation that should run on the fiber, because you should still run the interruption operations. What happens as an effect of running the interruption? What do you need to clean up? The interruption itself cannot be interrupted. So that's one of the reasons of those nested loops, catching, and again.
Yeah,
Wow,
I think
that's very impressive. So yeah, hats off to Mike and also especially Max, who's like considerably newer to this entire ecosystem, is now like battling with this end boss here. So that's really impressive. I'm looking forward to get my hands on this, probably mostly from a using and get to benefit from it perspective than digging into this myself and writing anything here. But this feels much more approachable now, given what we've learned over the last hour, with the fairly like simple mental model that Mike has motivated initially with sort of like a DSL of various operations, and that this is basically just a very sophisticated and powerful interpreter. And yeah, that makes sense to me now, how these other building blocks can build on top of it. So yeah, really fascinating. And I think hopefully this video will be a good resource for others who are like me or Harry, just curious about what this is about, and can learn about it this way. So yeah, I think we're closing in on time.
Can I ask a question?
But yeah, absolutely. Go ahead.
So since you define this interdependent computation and then hand it off to whatever the runtime implementation, does that mean that someone can define a program with effect and then benefit from future updates? Their program will become more performant potentially when you make changes to the interpreter.
Anytime we touch the interpreter at the low level, there is a huge change in both behavior, can be a huge change in both behavior and performance. For example, you can see one of the, Max, if you reshare the screen for just a second.
Yeah, sure. Hang on one second. I can move this window. Share screen.
Because let's see, for example, here, just open up the inner loop and go, for example, to a succeed or something like that. Above. of the nested one. Okay, for
Oh,
example,
sorry. Hang on. Let me go to the actual succeed operation. Hang on.
no, but that's okay. I don't need all of
There you
them.
go.
No, I actually want to see the nested one, the one inside the flatMap. Okay, so here you see, for example, in line 1225, this line has a t.parse nested.trace. Here we are parsing the trace, which is a string, to a more complex structure. Removing this line, or actually improving this line, removing the parsing at all, will be probably a 10% improvement on speed, which is something I was planning to tell you after, but given given that Harry back the question, anytime you touch a small piece here, you gain from performance improvement. Or if you do something dumb, you kill performance.
So there are a lot of opportunities to, without somebody making any changes to their program, benefit from updates to effect. That's really amazing.
Yeah, now the marginal improvements, it gets smaller and smaller and smaller over time, because this has been optimized over years of work in Zio. But the same program from Zio 1 to Zio 2, it's easier that literally the same piece of code would go twice as fast or 3 times as fast. That's highly probable.
Yeah, I mean, if you to get just a quick idea of like the massive performance improvements that the Zio guys have made on the fiber context. I mean, you see how lean the state that we're tracking here is.
There's nothing allocated.
Right, there's barely anything allocated here. Like the only thing I think that we're allocating like a state and a runtime config and maybe like a child set, but like everything else we're kind of trying to keep as much minimal information in memory for a fiber as possible. And if you look at the initial implementation, I have it here. I'm gonna make this bigger.
Way bigger, yeah.
The initial implementation of a fiber context had many different stacks that were used to track different pieces of information, such as like the current supervisor for a fiber, the scope, environment for fibers, the traces, there were a bunch of different stacks that were being kept around for in a fiber. And the really kind of brilliant move that the Zio contributors have made on the Zio side is to move a lot of this information into something called a fiber ref, which is a mutable, not mutable, but like a reference to a particular piece of information that can be shared across fibers. So for example, like the current environment of an executing effect, we now track in a fiber ref as opposed to like in the fiber itself. Same thing with things like the current fork scope override or the current loggers that are being executed, things like that.
And that means, for example, if you're not using the environment, that's not allocated. If you're not using override on fork scope, that's not allocated, and
right.
so on and so forth. It minimizes the state that is allocated inside the fiber. And every time you allocate, it's literally time in CPU.
So yeah, much leaner model of execution in the system next branch that hopefully we're getting closer and closer to something that people can actually test out.
I think it would be cool actually before merging this to build out a little set of performance benchmark tests and run it with the current version, and then also apply it to your new changes just to see like how much it is improved. And that also is a good foundation to just see how performance improves over time, hopefully improves over time.
And I mean, that some of that work has been done on the Zio side already. Obviously, it's not directly comparable with our execution in the JavaScript ecosystem, but their micro benchmarks have improved drastically on their 2.0 branch. They've seen massive speed improvements with the new Fiber context. So
or someone bought a new M1 in the meanwhile.
All running on the same hardware.
Yeah. So
all right, folks. I think this is where we should wrap it up. Thanks so much. This was really, really insightful for me. Learned a lot, solidified a couple of like other questions and concepts, and yeah, makes me more excited about using Effect. So thanks so much for all of your time, and see you in 2 weeks.
Thank you, everybody.
take care, guys.
Bye.
Take care. Cheers.